Good evening. All right, testing. Everybody hearing me loud and clear?
Yes, sir.
Okay. Yeah, I need to separate. I need to separate this thing. All right, I'm going to have to let's see who is here so far because it's a lot too much things to look at once. Let's see. All right, Andre, hearing me? That's
Yes,
Shante.
sir.
All right, I'm going to add you as a co-host. So I'm going to give you a job, and that's to add me to you. See coming in.
Okay, sir.
All right, thanks. All right, so let's begin. All right, so the main purpose of the session this evening, as you would have probably seen, so is to ensure that when we go into the physics exam, that we are getting all the marks that we need to, and that we are not losing marks for careless reasons. So that's the main aim. We're going to look at some past paper questions to kind of go through some of the points, and if we have time we can take some questions. Make sure. Keep this off. Done. All right. This is tangled up. Hold on. All right. Let's see if I'm. All right, good. All right, so for those who know me and know how I interact and how I teach, you know that I like when people interact. So don't be afraid to ask questions. If you need to raise your hands, that's fine. All right, so I am Mr. Moore for those who are not familiar. So some persons probably are not aware that I actually teach physics and chemistry. All right, and I am familiar with the process of marking. So I won't say too much on that, but yes, I am familiar with the marking process. I know some of the things that, right? I don't want anybody ask me to look out for them paper or anything like that, but we can go through some of that, right? So in terms of physics, there are certain things that have a bigger focus in physics. There are certain things that overlap. So the first thing in physics, as your teachers probably stress, is the graphing aspect. So paper 2, looking at paper 2. So see if I can go to. Alright, graphs. So then we go to a typical graph question. Alright, so not even just the question, just to look at how the graph is. So let me just go to a random graph. Alright, this graph now, so looking at this graph actually has some information. A lot of times, sometimes you'll see a blank graph. So both in all the sciences might have some kind of graphing component, but for physics it's the emphasis is on graphs. So when you look at the marks for a graphing question, it tends to be a lot of marks, right? So like as you can see, it's very small, but as you can see here is 8 marks just to plot the graph. If you should look at a similar graphing question in chemistry, it's probably 4 or sometimes even 3 marks to do a graph. Alright, so the emphasis is different. So when you are looking at past papers, you need to actually practice doing the graph. So a lot of people, when you're going through past papers, you skip doing the graph. Alright, so there are some important things to remember. Alright, in this one, they actually give you a title. So let me bring it up a little bit. So for this graph, they actually provide a title for you, which is good. So that's one less mark to worry about. So what are some of the important things we need to ensure when we're doing a graph? So let's see if we're ready for this thing.
Have to have the x and y axis.
You have to have the scale. Alright. What about the scale though? What about somebody mentioned scale? What about the scale?
Like the x and y axis, like the units, the centimeters to like units ratio or something.
Alright, so you need the quantities, you need the units. Alright, good. Anything else missing?
So you need a title.
Need a title. Alright, but in this case, one was provided. So make sure in the title you say very specific as to what you're plotting. So something very important, read the scale though. The scale should take up how much of the graph. So that's what I was looking for.
Like 75% or something. Or probably more than that.
Yeah, so at least 75%. So we can look at some of the issues that students tend to make. So these are coming out from some past papers. So when persons are plotting graphs, sometimes they use only a dot or only a circle. So note that you will lose marks if you do that. Alright? So don't lose silly marks like that. There's a lot of marks for the graph. So ensure you're using, these are what's acceptable for CSEC. Either use a X or use a dot. Alright, so in this it says the scale, well, we know about using rulers already. Nobody has to tell you to use a ruler at this stage to plot graphs. And if it's a straight line graph, we know about lines of best fit. So you hardly ever get a graph where all the points are, connected perfectly, right? So usually you have to draw a line of best fit where the points should be evenly distributed around that line, right? Among the lines. So you don't want it to be skewed. You want to draw a line of best fit. All right, even if it's a curve, for example, in radioactive decay, even if it's a curve, the line does not have to pass through all the points. You just need a best fit. All right, line of best fit. So do your best practice doing the graph. All right. And there's an important point in this section here. So let me go back to the past paper. All right, I think we know this by now that the graph in question typically gets a graph for number 1 can come from any section of the syllabus. So there's no limitation where that is concerned. So in this case, you see a transformer question being used, and transformer probably one of the last topics you would have learned, probably, well, depending on how your teacher organize it still. All right, so let's see if we can go through this one. All right, are we seeing clearly the paper?
Yes, sir.
All right, great. All right, so let's go. So transformers can increase or decrease the dash with a corresponding decrease or increase in dash. So, all right, so let's start with that. So if you remember the diagram of a transformer and the principle behind the transformer, what is a transformer used to do? So let's begin with that. Transformers. Anybody remembers what the transformer is used for? Or the purpose of it?
Step up or step down current.
Step up or step down. What's the quantity? Voltage. All right. So voltage. All right. So in terms of the transformer equation, so if you remember the equation, it helps you to remember the principle behind it. So you can either put the primary or the secondary at the top. It's up to you. So, and let's put the primary at the top. No, secondary. Let's put the secondary at the top. So All right, this look familiar. This equation looking familiar. Yeah. No.
Yes, sir. It looks familiar.
Okay, great. All right, so we have on the, if you remember the transformer diagram, you would remember that you have this box, like this hollow looking box, where on one side of the left hand side of that box you have some wires being coiled around that side. So we talk about number of loops or number of turns, the amount of times we have that happening. That's what n represents here. So n is the number of turns of the coil. Then we know V is voltage. And I is current. So yes, there's a relationship between them, between the three of these. All right, so what this means, just looking at the equation, if you have 500 turns in the 500 turns in the primary, so let's start with the primary. If you have 500 turns in the primary and you have 1,000 turns in the secondary, so I'll show you how easy this is. You have 500 in the primary and 1,000 in the secondary. If you start out with an initial voltage of, let's say, 12 volts, what's going to happen to the voltage so this is the voltage in the primary. So if your primary voltage is 12, what's going to happen to it on the secondary side?
It will be double.
So it will become so it will be
24
volts. All right, so that's it. There's a direct correlation between the number of turns, the ratio in the number of turns on the secondary and primary with the ratio of the voltage. So if you double the number of turns, you are going to double the voltage. All right. But what you notice about this side, the current, what's the relationship with the current though?
It's the reverse. So it's primary over secondary. Inverse proportionality.
All right.
Proportionality, yeah.
All right. So that means
directly.
So that means that if you start off with 10 amps, that means that at the end of this process, you're going to end up with 5. All right. So the principle is based on an ideal transformer. Well, the ideal transformer, we talk about power. So if energy is conserved, if there is no loss of energy, no loss of power, then the power before or the power in the primary should be equal to the power in the secondary. All right, so that's the principle behind it. So conservation of energy. So if you step up the, let me put actual values to this thing. So let's say the power is 100 watts. If the power is 100 and you have an ideal transformer, the power in the secondary is going to be 100, so it shouldn't be any loss of power. All right, so that means that when you multiply the current times the voltage, it should give you 100. So if you step up the voltage, if the voltage was 10 before and you step it up to 20, when you multiply the voltage by the current, it should still give you 100. So the only way that is possible, so think about it mathematically, only way we could get 100 in the first case is if the current was 10 amps, and the only way you could get 100 in the second case is if the current is 5. Alright, so if one goes up, the other one has to go down. That's conservation of energy. Alright, so let me go back to the image question. Alright, so transformers, so it says should go on the first line. So transformers can increase or decrease the voltage with a corresponding decrease or increase in what should go on the second line.
Current.
In current or the number of turns. Which one is it? With a corresponding decrease or increase in number of turns.
Sir, couldn't it be either? Because both of them are directly proportional.
The current and the number of turns?
Yes, sir. It could be either of them because both of them are directly proportional to voltage.
No, man, only one of them is directly proportional. One of them is inversely proportional. Alright, one of them is inversely proportional. So current is inversely proportional. Alright, and then the basic principle behind the working of a transformer is the phenomenon of the what's the principle? So conservation of energy. All right, all right, so look at this diagram. Without reading anything, we can just look at the diagram for the transformer and we can look and tell what type of transformer it is. So based on the diagram, what type of transformer is it? It's a step one?
Step up.
Is it
Step up.
step up? So
Step down.
Step down. Step down, yeah.
Alright, so it's a step down transformer. Because when we look at it, we see there's a higher number of turns on the primary side. So they even gave us a value, 3,960 to 600 turns. So they have that in common. Alright, so it's a step down transformer. So let's see what. So in the experimental setup shown in figure 1, a variable AC voltage source V1 drives the primary winding of an ideal step down transformer with a turns ratio of 3960 to 600. And they give you a resistor which is connected across the secondary windings. Alright. So you're given a table with the values for V1 and V2. And then you would have to plot that graph. Alright, so since we're not able to plot the graph, let's do a shortcut. Don't do this in real life. So what we can do is use the values. So we're plotting V2 versus V1. So let's take let's take the second value and the second to last value. So the 10 and the 1.5 and the 60 and the 9. As I said, don't do that. When you're doing your gradient, you draw your triangle. We know how to do that. Make sure that the triangle takes up more than, I think it was about 50% of the line, if I'm not mistaken. And use those values that are on the triangle to do the gradient. So since you draw a line of best fit, these values don't have to be in the table. Alright, but I'm just using the table so that we can get a gradient value. So it would be, it would be what, 9 minus 1.5. Nine minus 1.5 over 60 minus 10. Alright, so somebody worked that out quick and fast. I hope somebody have a calculator right next to them. So that's V2 versus V1. So V2.
So 0.15.
So that's 0.15.
Sir, what is that number beside it? 1.5.
Oh, the 9. Sorry, it's supposed to be a 9. This one. Alright, would it have a unit, by the way? Would it have a unit? This is our slope. So of course not, right? It doesn't have a unit, right? Right. Since it's voltage against voltage, so it would be unitless. So the value that we get, that's one of the questions, one of the following questions. what does the slope of your graph represent? So if you're plotting V2 versus V1, and we just did that, and we did our gradient, you will end up with 0.15. So what does that value tell you? What's the significance of that value? Does anybody know? If you plot V2 over V1, what is the significance of that? All right. All right, so like we're unsure.
Very unsure, sir. Very unsure.
I think so never mind.
Never mind. Okay.
Sir, does it give resistance?
If it gives a resistance, no. Mm-mm. Mm-mm. All right. So what it's lit art. I should have probably stated this before. So for any graph that you plot, and you're required to do a gradient, just think back to the equation that it's linked to. So always think about what's the physics equation that it's linked to. So you are plotting V2. What's another term for V2 in this case? What would be another term for V2?
Final voltage.
The final, or in the language of transformers, what would that be? Since we're talking about transformers.
Secondary voltage.
Yeah, so that's the secondary voltage versus the primary. So that equation would be, it's literally this. Is this is just plotting Vs, or in that particular question, Vs over Vp. V2 would be the same thing as Vs and Vp. So for any graph that you're given, let's look at what's on the y-axis and look at what's on the x-axis and see which equation it is linked to. So all this does is it tells you the factor. See this 0.15 is just the factor by which it will be stepped up or stepped down. Right? It's just just that ratio. Alright, so it's not going to give you resistance. The only time it could give, which equation will now have resistance in it? Since somebody mentioned resistance, yeah.
V.
So V is equal to IR. So in that case, you would have to, if you're plotting a graph of V voltage versus current, let's traumatize it with a little maths. Y is equal to mx plus c. In this case, if whatever is on the y-axis, of course, is y. Whatever you plot as x is x. So in your equation, whatever is directly beside x is automatically your gradient. Alright, and plus c in physics, the c is usually 0. So you're usually drawing a line through the origin. So it's usually just this. Alright, so watch exactly what you're plotting. So practice the graph questions as well. Don't ignore the graph questions when you encounter when you're going through the past papers. Alright, we don't have a graph. All right, so remember that value for the V2 over V1.
Sorry, sir. Which question are you doing?
We are looking at E. All right, so, okay. I don't, we can't do A since we never did the graph. So you would have to do the graph to do E properly. We could use the value that we just got to, since we know the ratio, they say if V2 is equal to, sorry, if V1 is equal to 50, what is V2 likely to be? Even though we didn't do the graph, if V1 is 50, what is V1 likely to be based on what our gradient was? So let's see if somebody can work that out. If V1 is 50, what is our gradient likely to be? Not gradient, what is V2 likely to be? So let me help you out a little bit. So
It's 7.5 when I worked it.
7.5.
Yeah, I worked it out at 7.5 volts.
All right, so how you did that? How you did?
The formula is V2 over V1 equal 0.15, and since you know that V1 is 50, I just replace that and I multiply 50 times. Well, I multiply both sides by 50, and it would be 0.15 times 50. Yeah.
All right, so you transpose. All right, great. All right, but in a case like this, though, if they say use a graph, use a graph. All right, so sometimes, so this is, at least you know what the value should be, but again, use a graph. All right, I don't want to. All right. The next question: calculate the current I2 when in the secondary winding when V1 is 50 volts. So it's related. It's a follow-up question. So V2 is, you said, is 7.5. That's what you said.
Yes, sir.
So V2 is equal to 7.5 volts. So how would you determine? Yes, does somebody have a question? Or
Is there a resistance value?
if there is a resistance value, there is a resistance value. Okay, so what are you thinking about? Why you ask about resistance?
So V2 equals to I2 times R2. So transpose for I2, it's just going to be V2 divided by R2. And then you substitute those values. Which is 10 amperes.
I see. All right. I see where. All right, let me take down all of this. All right. So, by the way, everybody was following as she was talking. Everybody understand what she was saying?
Yes, sir.
All right. So just
Yes,
to
sir.
No, sir, no.
all right. So all right. For in this case, the resistance we didn't need a resistance to calculate the current here, right? For because we know V2 and we know V1. Um,
Oh, no, I get it, sir. No, I get it.
you get what you're saying?
Yeah, I'm seeing it. Yeah.
Oh well, let me go. Hold on. All right, the current. All right, so we know V is equal to IR. Good. We have the relationship. Put this to the side. Sorry, why I have two S right there? Over IS. All right. I thought they gave you a power rating, but they didn't give you a power rating. So if we want to find the current, we'd have to use the V equal IR. So that's fine. So the current in the secondary winding would be I equal V over R. So the voltage is 7.5 and the resistance is 5. It was 5, right? Let's see. 5 ohms. Yes. All right, what that work out to be?
1.5.
1.5. All right, so 1.5 amps. One, two, three. All right, in terms of the mark breakdown, so for all calculation questions, so for those who just like to jump into calculations, please note that there is a mark for stating the equation that you're using. So it's state, then substitute, and then solve. So that's typically how the marks are allocated for calculation questions. State the formula. So even, well, I won't say that, but so state the formula, do your substitution and get the answer, of course, with the unit. So don't want to lose marks just because you want to rush into the question. All right. Another thing to note, a very important thing to note in terms of it's a secret but not really a secret in terms of how the marking is allocated. So you are, well, depending on the circumstances, and most circumstances you are not penalized twice. All right, you are not penalized twice. So if you make a mistake in a previous question, so let's say for this you got 750 for your V2 instead of 7.5 or some madness, right? Then if you go ahead and use that value in F, the answer for F might be wrong. So when the solution might be wrong, but because you use that same value, that will allow you to get full 3 marks. So I generally tend to advise people, even if you're unsure about something, still go ahead with it. Avoid leaving things blank, because you'll be surprised about how you can pick up marks on these things. All right, so your answer can be wrong and you still get full marks for a question. All right, it's a secret, but not really a secret. All right. Use the slope of the graph and the equation to determine. So this one pretty simple. Or the current that we just found was, you said 1.5 amps. So use the slope of your graph and the equation I1 equal S times I2 to determine I1 in the primary winding. All right, so it's just that the slope was 0.15, and I2 was 1.5. All right, so what would that work out to? So the slope was 0.15, I think. Yes, go ahead.
0.225.
So 0.225 amperes. All right, this one, power dissipation. Calculate the power dissipated. So if you see power dissipation or power loss, there's a particular equation for that. What is the equation for power dissipation? Anybody knows that one? What's the equation for power?
Sir, do you calculate the power before and after? And then minus?
The power before and after. No. Yes, somebody has something. I hear a hand. Who is that? I hear it.
Oh, sir. Is participation P equals V times I?
I swear.
Alright, so no, it's not the regular P equal IV. It's not that one. So if you need to make a note of this one, you can. So we know, so P equal IV, that's electrical power. But in terms of power dissipation, P equal I squared R. Looks familiar, yeah? Oh, okay. Yeah. So make a note of that. This is power dissipation or power lost. Alright, so they calculate the power dissipated in the resistor. So what would I be? So this one was I2. That one was I2, or this one was I1. Yeah. Which I are we using for this one? Which I would we be using? Because it's two different I's. Which I's? Is it I2 or I1?
I2.
I2. You know why you say I2, or you're just saying I2?
Because what do you call it? The resistor is over the side with I2.
Exactly. So the resistor is in the secondary windings, connected to the secondary windings. So it has to be the current that's flowing through that particular section. So that's the one we're using. So I squared would have to be 1.5 squared times 5. All right, what's the maths on that?
11.25.
All right, 11.25 watts. And that's it, 3 marks. All right, and by the way, I don't think I needed to say it, but let me say it just in case. Sometimes they give you tables to complete. We know that when you're inputting values in the tables, you have to ensure that you're watching the number of decimal places. So even if you get like a value of 10 flat, you want to keep the decimal places consistent. So if everything else is in to one decimal place, you'd have to say 10.0, right? You might think that that's trivial, but things like that will cause you to lose marks. All right, was that the last question? Oh, power. Determine the power input to the primary windings by the source. So now we can just do the power. So P equal IV. What was the initial voltage? Again, 50. P equal IV. All right, the initial all right, so it's just P equal IV, and you input your values there. So at the source it would be 0.225 times 50. And that would give us our power. Alright, what's the math on that one? So
11.25.
11. Hold on. Okay, yeah, V1 was 50. Alright, an elevator raises a group of 12 persons through a vertical height. Oh, somebody have a question? Had a question?
Sir, can you remember what year past paper this is?
This one is, I think this is 2025.
Alright, sir, thank you.
Hold on, let me check if it's January. Yes, it's January though. Alright, an elevator raises a group of 12 persons through a vertical height of 10 meters in 5 seconds. If the average mass of the persons in the group is 55 kilograms, calculate the gravitational potential energy. And what's the formula for that?
MGH.
So EP is equal to mgh. So the mass would be just it would have to be the 55 times the 12. Yeah.
Yeah, yes, sir.
And we have the height, and so it's just a matter of multiplication. So somebody do the math on that. MGH, G is 10, and so what's the energy? So 55 times 12 times 10 times 10.
$6,600.
What? No, that's how I got. I got 66,000.
That's what I got as well.
66,000. 66,000 joules. Okay.
Oh, sorry, sir, I put in the wrong thing.
Okay, so that's the alright, so that's the potential energy. So what would be the power required to raise the group? So generous. That's the equation for power we use in this one.
Time times energy.
10 years right now.
What's
Energy over time?
energy over time? Okay. Yeah. Yeah. So we have the time, 5 seconds. So you just do your math. Just do your math. All right. Somebody, you work. What you got?
Yo, sir, 4 marks for that.
Yeah.
What?
Yeah. They're very generous over physics. Very generous.
I got 13,200 watts.
13,000.
200.
Yup. All right. In terms of, all right. So let me look at. Let me quickly just jump to 2021. Same question one. So in this case, here's an example with where the tables were. They had to fill out tables, and it was a lens. It's a lens question as the graph question. All right, so we could potentially do the. All right, just tell me the values. We'd have to insert them. So we have u. We have u here, and we have v. In in terms of lenses. In terms of lens, the lens formula. So let's use that as our basis in terms of lens. The lens formula is 1 over f is equal to 1 over u plus 1 over v. What is the u and what is the v in the lens formula? Alright, so we're not study that yet. So v is, u is the object. So anytime you see u, it's either some object height or object distance, depending on the context. And v, how I remember it is I say v for virtual, in terms of like a virtual image. So I have v's image. Alright. Whoops. Oh, that no. Alright.
Sir, what formula is this again?
So this is the lens. So when you're dealing with when you're dealing with lens, so the converging lens or diverging. Alright, f is the focal length. Let me not assume that. You know that. Alright, so let's do at least the first row. Alright, let's do at least the first row. So what would be 1 over u? So just some simple calculations. What would be 1 over u in this case? So put that in the calculator. If you put 1 over u, what would you, for the first row that is, what does your calculator tell you? Zoom in.
Let's say I got 0.05.
So you got 0.05. Alright, so what should go in this column, the first cell or the second cell, the first missing cell?
0.5.
You say you got 0.5 or 0.05.
So you said 0.05, but if you put 1 over 30 at 0.033,
Yeah.
have 2.3 there. So
Yeah. Alright, so so there's a reason why I went to this question in particular, because CSEC said a lot of persons messed up this question. So what are we ignoring? Let's say, what are we ignoring in this, for this particular table? I can't ignore it. So look at the headings. What's the important thing in the heading there?
Times 10 to the negative 2.
Yeah. So there's a times 10 to the minus 2. So that's why when you put your value in the calculator and you get 0.05, then you have to convert that so that it fits within that. So you'd have to move the decimal place 2 times if you want it to fill in this slot. So that first value here is going to be 5.0. Alright, so it's 5.0 is it should be our first value. Alright, and according to the report, even when the persons were plotting, so persons lost marks for this when they plotted. Alright, so that'll be 5.0 and then 1 over 60. What would be 1 over 60 then?
Wait, sir, can you repeat that part?
The part about the heading, the times 10 to the minus 2, and what to do?
Yes, sir.
No, so I'm saying that the times 10 to the minus 2 is an indication that you need to move the decimal place 2 times. In this case, 2 times to the right. So if you got 0.05, then when you move the decimal place 2 times to the right, it should get the value. Alright, so or I can say it a different way. 5.0 5 times 10 to the minus 2 is 0.05. Alright, so whatever value you put in the table, when you multiply it by 10 to the minus 2, should give you that value. So that's another way of saying it. Alright, so 1 over v, so sticking to the first column, 1 over v in that case would be what? So when you put 1 over 60,
1.7.
alright, so 1.7. So 1 divided by 60 would have been what, 0.0166666, alright? So alright, so that's good. So 1.7, yeah, 1.7. Alright, so stick to the decimal place, so that's good. All right, so in terms of the graph, you're going to end up with should have a graph somewhere. Somewhere here. Alright, let's see how their blank graph. So they have a graph like this, so they drew the axis lines for you and give you a title. Alright, it's not every year you get a title, so look carefully if you're actually given a title or not. So your graph, if you plot the graph, it should end up looking something like this. So this is what I saw, kind of blurry, but should be a line of best fit. Alright, so this is someone's attempt at drawing the line. Alright, so according to the report, a lot of persons would have. So we know that you're supposed to label the axis. So you're supposed to label the axis, quantity and unit. Alright, in this case, you would have lost marks. So if you use like the integers there, like the 1, 2, 3, 4, 5 to plot, you would lose marks if you didn't put the times 10 to the minus 2 on the axis. Alright, so things like that can cause you to lose marks. So you'd have to put times 10 to the minus 2 if you're using the integers as is. Same values in the table. Alright, is there anything else of note for this question? Alright, so this question would have required you to just look at the intercepts. So they wanted you to look at the graph to determine what the intercepts are. So there are two intercepts. Alright, what are the values? Let's do an estimation based on what you're seeing here. What would be the value for the y-intercept? So just based on, let me go up a little because you can't see that. What would you estimate the value from this graph to be? Yes.
0 to 6.8.
6.8. Well, you said
6.7.
6.7.
7.
Gosh, 6. So 6 point. All right. If you use, I think somebody was actually using the decimal earlier. So if you use 6.7, then you'd have to say times 10 to the minus 2, same, to the minus 1. If you're converting it, you can use a decimal. Alright, what about the other axis? The other intercept, I should say.
6.5 times what the was
6.5 times 10 to the minus 2, same to the minus 1. Alright, and you would have to average that. So 6.6. Alright, you'd have to average those. So our value for C. So let me show you what you were answering just by doing that. So looking at the axis, so where the line crosses the y-axis, that's about 6.6. 6.7. Where it crosses the x-axis, that's about 6.5 times 10 to the minus 2. So this was the follow-up question to that. So use the graph to determine the intercepts C1 and C2 on both axes and calculate the average value C. So that's what you're doing for 4 marks. And then they gave you a formula. You'd have to use what you just did to calculate 1 over f. So use the formula C equal 1 over f to calculate the focal length of the lens. Alright, so what we say C is again. So it's the average of C1 and C2. So what would C be equal to in this case? C equal 1 over f. What's the average of 6.5 and 6.7?
6.6.
6.6. Alright, so C would be 6.6 times 10 to the minus 2. Alright, so how would you determine the focal length? So that would mean f is equal to what?
1 over c.
So f would be equal to 1 over c, so we'll do the inverse. Alright, so we can put that in our calculators now. So 15.15
centimeters, I think.
Alright, centimeters. Alright, so C, the unit for C would have been SM to the minus 1. So if you're doing the inverse of that, why I put minus 1 over this one, with who knows. Alright. So that's the focal length. Alright, and then the last question in that, for that particular question, is just to complete the little statement. Alright, so the principal focus, say you would have to know what the principal focus is. That thing, that point. Well, may I give you the answer. The principal focus of a concave lens is defined as the dash on the, anybody knows what the first line, what should be on the first line? It's the dash on the principal axis from which rays originally. So the principal focus is what? What's on the first line? What do it look like to you?
Point.
Alright, so the point defined as the point on the principal axis from which the rays originally. Alright, again, you'd have to know this one. You'd have to know how the thing works as it goes through the lens.
Converge.
Converge. No. Well, look at the type of lens too. So they actually told you the type of lens in the it's a concave lens.
So diverge.
Diverge. Yes, so diverge is a part of it, but it's not for that line though. It's not for that line. Alright, so for the second line, if you remember how they, I'm trying to remember if I have an image of that. Hmm. But the lines are parallel, the rays are parallel. Once they go, once they're at that lens. Let's see if I have an image for that. No, it don't look so. Alright, so on the second line is really originally parallel. Alright, so the rays are originally parallel to the principal axis, and then they do this after, and then let's see if we can, you might have to use more than one word for that third line. So to the principal axis.
That'll be diverge.
So yeah, you can diverge, or some people might say appear to diverge after passing through the lens. So yeah. Alright, so let's talk a little bit of a strategy for this thing. So I know nobody here falls in the first category, nobody here, but I'm still going to talk about it. So the people who might be worried that you know they're worrying about passing physics. I know that's nobody here, so I'm preaching to the choir. It's going to depend on the approach. Of course, the fact that you're here means you have intention to more than just pass. So we're already over the hurdle as it relates to SBAs and whatever. We already secure good marks, so I have nothing to worry about. I'm going to secure as much marks on the paper one as we can, because paper one, it's a pattern. If you look at the trends, there's not, once you practice, that's not the problem. The problem is going to be paper two. So you have to focus on getting paper two right. So there are some topics that I think are easier to go through than some. So I would probably suggest going through some of those easier topics first. So like I think section E, which is the nuclear physics part. Let's see if I'm right or I'm wrong. Nuclear physics, waves. I would make sure to maximize marks on those. You have things like electricity and electromagnetism that might be a little, but let's have a good strategy. So what I'm going to let me see if there's anything on the report that I did not highlight. Alright, so make sure that you're using your syllabus. Right, and some of you have your past paper book, the physical one, which I prefer. But if you have an online one, that's fine. Just make sure you're not distracted. Make sure you're actually writing. So if you're using online papers, make sure you're physically writing something. while you're attempting them. Alright, so what I would do, one strategy that I would do is just scan through the syllabus and look for all the laws and the principles that you need to know. So the first one there, principle of moments. So somebody remind me quickly what the principle of moments is about. What's that? It's principle of moments. Yes, go ahead.
Oh, the ability of an object to complete the movement around a fulcrum when a force is acted upon it.
That's the principle. That's the principle.
Rotation.
Is that the principle though? The principle. It's so like you're describing moments a bit, but is it that the principle of moments?
Oh,
What is the principle, the actual principle? What does that state? It states that anybody else can assist. Yes, go ahead.
So it states that the anti-clockwise moment is equal to the clockwise moment for a
So
body to be in equilibrium.
for a body to be, or you might need to rearrange that a little bit. So let me see. I think there is a question here. So this was the question, yeah. State the principle of moments. You notice how many marks for just stating the principle of moments? 3 marks. So you'll have to make sure that it has everything that they want. So it is for a system that's in equilibrium. Alright, so the system has to be equilibrium. That's 1 mark for mentioning that. Alright, if you don't talk about the fact that it's in equilibrium, 1 mark is gone. Alright, so for a system in equilibrium, then you can talk about the sum of the clockwise moment is equal to the sum of the anti-clockwise or counterclockwise moment.
Yes, sir.
Yes, go ahead.
Sir, do we also have to mention if the moments are about a point?
Yes. All right, so
Okay.
that would be the 3rd mark. All right, so that's why I say make sure you know the laws. So I would go through all the laws that are in the syllabus and just take them out of each topic and make sure you know them. Alright, so the laws, the principles, so whether it's conservation of momentum, we know about energy, make sure you can state them clearly. And so on. Alright. Oh no, wrong thing. Alright, so I am handing it over to you. So in terms of, you can select a topic that you want me to you think you'd want me to look at in the time that we have left, a topic or 2. So what you think is, which one is burning? So we have some topics here on the left. We have circuits, electronics, lenses, and anything burning, electrostatic, electromagnetism, atom and radioactivity. Somebody saying something?
Yes, sir. Can you go over heat energy and measurements and transfer?
Heat energy. All right. All right. What I will say about this one in particular. So probably the first thing that comes to mind is, as you see here, MC delta T and MLV, and so latent heat, specific heat capacity. Those are the things that probably come to mind. All right, so sometimes they give you some questions, some of these thermal energy questions, or heat transfer questions that involve both the energy associated with change in state and the energy associated with change in temperature. So you have to make sure you're reading the question properly, because sometimes you have to add both to get an answer. So if you're changing just the temperature, so if they tell you that they take out ice out of the freezer at negative 10 degrees and they leave it out, right, and then it eventually reaches let's say 20 degrees. It's not just MC delta T that's involved in the change right there, because it had to undergo a change of state. So make sure you are looking at that. So these are some concepts. So we have those. We have the methods of heat transfer, convection. That's the transfer through a fluid. So that's a liquid or a gas. That's the transfer of heat. Conduction, we know it's when it's in contact, direct contact. Go ahead.
Oh, good night, sir. Would you be willing to share this document?
You don't have this already? I thought you had this already.
No, sir.
Oh no. Okay. All right. I think if you're in the Google Classroom, I think something should have posted. Something should have been posted a while ago. Not a while ago, like an hour ago. Or if it didn't, yes.
Sir, when did you have a Google Classroom?
When did I? No, you have one. I will share that one. But hold on. What did I do with that? You can probably screenshot this page or something, or use the QR code. I think it should still work. Let me check if it still works. So I'm going to put some more resources there, but for those in the Google Classroom, that's where I'm going to be adding some resources. But those who already have the physical book for this, you already have those, what I was showing you a while ago. So if you have the physics book by topic, you already have a lot of these notes. So does the QR code work? Does it work? Yeah? No? Or nobody don't try? Alright.
So I'm gonna try it, sir.
You're going to try. Alright, but anybody in the VS room actually see something about physics and chemistry resources?
Yes, sir. Yes, sir. I see.
Okay.
Thanks, sir.
Okay. So I should take it to the same thing. is.
Yes, sir. It worked. The QR code worked.
Alright, great. Alright, this is so pale. Alright, so let's see how quickly we can do this. So a block of ice has a mass of 2.5 kilograms and a temperature of minus 10 degrees Celsius. So it is placed in a container. I think we did read that right, but anyways. So they gave you the specific heat capacity of water, specific heat capacity of ice, latent heat of fusion of ice. Calculate the heat energy required to change the temperature of the ice at minus 10 degrees to ice at 0. So what's the equation? What would be the equation for this one? Yes, go ahead.
Educated guess MCAT.
Right, so this one is now changing temperature. So there's no state change. Right, there's no state change here, so it's just one here. So you state the formula. E H or E is equal to MC delta T, and you would input your, make sure the quantities are in their SI units. So I think we're good here. So it would be 2.5 times what's the specific heat capacity. So what would you input in the calculator? Well, yeah, what's the specific heat capacity here?
2.1 times 10 to the power of 3.
Right, so that's what, 2,100. 1, 2, 3. So it will be 2.5 times 2,100 times the delta T, and the delta T here is, so what's T final? T final is how much? In this case, so if we're calculating delta T is T final minus T initial, right? So what's T final?
Zero.
So T final is 0. So 0, and what's T initial?
Negative 10.
Alright, so that means that delta T is going to be?
Negative 10.
Negative 10.
Delta T is negative 10. Are you sure about delta T is 10? So T final minus T initial, right? So that's delta T. So that's going to be the final temperature. You took it out at the fridge at minus 10. So T final minus the initial temperature is minus 10. So, all right. We don't need to convert the temperatures to. Sorry, repeat.
It becomes positive 10.
Yeah, right. So it will become positive 10. I was asking, do we need to convert this to Kelvin, by the way?
Oh, no.
No.
Alright, so, right, we wouldn't need to convert this to Kelvin, because a change in Kelvin is the same as a change in degrees Celsius. So once we do the change, that's good. Yeah, so Yeah, multiply that, that will give you a value. So somebody do that so 2.5 times 2100 times 10. What's that value? That's it. What does that work out to?
52, sorry, 500, 52,500.
So 52,500 joules. All right, they're so nice this year. They're not always this nice, right? So sometimes they ask you to calculate the energy in one step, but in this they've just so broken it down so nicely for you. So how would you determine the heat energy required to convert all the ice at 0 degrees to water at 0 degrees? What
Latent heat of fusion of ice.
Latent heat of vapor.
of fusion
No,
of fusion, man. So that's MLF. So so 2.5 times the
Japan, lock your mind.
well, yeah, I hear something. Yeah, so 2.5 times the 3.3 times 10 to the 5. And that would give you, all right, so what does that work out to? So the energy to change the state of from ice to water is
So what's the formula for latent heat of fusion again?
no, so the formula for the heat energy is ml, so it's just the mass times the latent heat of fusion. So so remember I had highlighted earlier, so there are there's one for temperature change, the MCAT, and there's one for state change. There's an energy associated with state change in the state. Yes, go ahead.
825,000.
825. Oh, 825,000.
I converted the latent heat of fusion. Sorry.
Yeah. All right. So yeah. So the answer should be in joules. So well, the answer is you want the answer in joules. They didn't specify any other unit, so that's fine.
So if you could have put it in kilojoules, that would be fine as well.
If they would accept it,
Yes, sir.
no, keep it in the SI unit. Keep it in the SI unit,
Which will be joules, right?
which would be joules. So unless they ask you for it, just keep it to be safe, to be very safe. All right, the water in the container is now heated to 80 degrees Celsius by an electric heater in 600 seconds. Calculate the power output of the heater. All right, so it's a follow-up question.
For English,
P is equal to W over T, or work over time.
So that's power, yeah. So energy over time, but what energy? Where we get the energy from? What's the energy?
Latent heat.
It's latent heat for this one. You look at what you're doing. You're heating water to a temperature of 80. So the water in the container to a temperature of 80 degrees. Go ahead.
I don't think it's latent heat because it didn't state any state change, so it would just be regular heating.
So MC delta T, right? So unless they could have what I have seen them do that they have asked about like the energy to boil off, so to boil off a certain amount of water or a certain mass of water. Now in that case you would have to consider both the raising the temperature and latent heat of vapor, the energy to change the state. Alright, so you'd have to use MC delta T, so the M still 2.5, the C, what's the C here? What would be the C again?
The 4.2 times that.
So 4.2 times 10. So 4,200, which you know is the specific heat capacity of water, joules per kilogram. So it's water, no, not ice. And then delta T would just be the 80.
Or just 80.
80 minus 0, right? So, alright. So that is what you would do. Alright, you get your 3 marks. So state your equations, and I mean this could have only 4 marks. Yes, go ahead.
Wait, what's the mass?
Oh, who first? Somebody first. Who first? Our ladies first. Go ahead.
1,400 joules.
1,400 joules. Oh, so that's your calculation. 1,400. Why that sound low? That sound a bit low.
I was asking if the mass was stated earlier in the question.
It's the same mass, so the question is linked. So the mass is 2.5. So
I just recalculated it. It's the same number I got.
1,400 as in 1400.
Yes, sir.
Okay, scroll up. What was the mass again?
2.5.
So wouldn't that be 2.5 times 4,200 and you multiply that by the 80?
Yeah. So that's why you got 14?
Well, when I did it, I got 140,000.
140,000?
Okay, sir, scroll up to the specific details.
Right, so it would be 2.5 times 4,200 and multiply that by 80, which is a change in temperature, right?
Am I seeing this correctly? What?
Times 2.5.
That's times 80.
Why my answer look different from everybody's answer?
840.
800.
Divided by the seconds, right? So how much seconds is it again?
Oh, you're giving me the power value and not the energy value. Maybe I have to clarify now, because I thought you were giving me the power value. I mean, not the power, the energy value. Because if it's the energy, I got 840,000 joules.
Yeah, I got that as well, sir.
Yeah. And then divide it by the 600 seconds, the
14.
1400 what she got.
So the 1400 was the watts then, was
Yeah.
the power.
Or the power, yeah, so what?
Okay. Alright, makes sense now. Makes sense. It's all coming together. Alright, state one assumption which must be taken in C1. Or would have to be an assumption.
Assume that there is no heat energy loss to this, or
No heat loss to the surrounding.
No heat loss to the surrounding. We all agree with that.
Yes, sir. Yes, sir.
Alright, so that's how you would deal with those type of questions. As I said, the other type of heat transfer questions can be in the form of like asking about convection, radiation, and let's see if I can find. Alright, this one is a very blurry, but it can tell me. Let me just read the description and you tell me which mode of heat transfer it is linked to. So the description says transfer by medium movement. So so we have conduction, convection, radiation. Transfer by which one?
Conduction.
Conduction. Or convection. Conduction. Medium movement.
Yeah,
so
transfer medium.
Alright, we're gonna come back to this. Transfer without a medium then is which one?
Radiation.
So transfer by electromagnetic wave is what?
Radiation.
Still radiation. So transfer without medium movement.
Yeah, wouldn't that
Conduction.
yeah, that would be good conduction.
Conduction.
And the transfer by
medium movement.
Yeah, what else? Yeah, exactly.
Would be convection.
Yeah, convection.
Let me say 106. Page 106. So let me just show you the image. What was that again? I thought it was the other image, but yeah, in convection the medium has to the movement. In convection you have movement by densities. So like the water, for example, the water at the bottom of the pot is going to have a lower density and it's going to rise, and the denser water is going to fall. So you have this circulation of the medium. Alright, so make sure you're clear on the distinction between the three. So let me go back to 106. Why it look like it? Transfer by physical contact. That one is obviously which one?
Conduction.
That one is conduction, and transfer through liquids and gases.
Convection.
Convection.
I agree.
Alright, so yeah, that's it. That's it. So I don't think we should have any problems with that. I would say one thing I would say, don't ignore like the thermometer stuff. So in terms of knowing what the upper fixed point is, knowing what the lower fixed points are, the different types of thermometers. So definitely don't ignore that. Alright, and the principle that they're based on. So
What do you mean for thermometer?
thermometer. You didn't learn about that? Yeah, man. Different types of thermometers. So thermocouple. So like the laboratory thermometer, the thermometric property, as you can see here, is the volume. So the thermometric property is something that we can measure that is directly related to change in temperature. Right? So the liquid in the thermometer, the laboratory thermometer, expands or contracts with. Alright, so you have to be familiar with these. So you have the resistance thermometer and its property, you have thermocouple and its property, and those things. Alright, so this is a good one to know. Good set of things to know. Alright, so yeah, man, you guys will be fine. Just make sure you study. Some of you know that I'm doing 2 more sessions next week, but those are actually marathons. So we'll be trying to go through as many questions across the topics as possible. So at least one from each. There are some topics that are rarely tested, so it's kind of organized by, as you see on the left, it's kind of organized by the popularity a bit. So atom and radioactivity, you have to make sure you're strong in that section, and I think it's a good section to maximize marks on. Electromagnetism, fairly common. Electricity, heat, fairly common. Waves, of course, can't ignore waves. Alright, so Snell's law, optics, Lenz's law, Lenz formula. Well, I separated it in this, but yeah. So I'll try to go through as many questions from different topics the next time that we meet. So some of you will be coming back next week. I think it's next week. I think I'm doing chemistry first. Let me not give you a wrong date.
I'm seeing we have chemistry for the 26, it says.
26. No, that chemistry session is something similar to what we did tonight. So that one, that's not the marathon session I'm referring to. So that one is 6 hours long.
The first marathon is on next week Wednesday.
Next week Wednesday and Thursday. No, it can't be Wednesday and Thursday. Or is it?
I'm seeing we have marathons for the 29th. Is that Wednesday?
That is Wednesday.
Yeah, that is Wednesday.
Yeah. So it's 6 hours. That's 6 hours. So I don't advise doing 6 hours one time, so I just split it into 2 days. So 6 hours across 2 days. So that's what we'll be doing. Alright, so for those who do chemistry, we're doing a session like this on Sunday, Jesus, my brain. On Sunday, 7 starting at 7. So a similar session to that, similar 2-hour session. So if you want to join that, feel free. We're using the same link to do that session. So don't lose this link for those who do chemistry. Alright. If any other questions, they can reach out to me. You have the information there. Reach out to your teachers, but make sure you're practicing past papers. Make sure you're being strategic about it. So as you study, once you go through the syllabus and you say, all right, going through radioactivity today, and you do some practice questions on radioactivity or on nuclear physics, then you should be good to go. Yes, there's a question. All right, so.
Sir, can you go back on the QR code?
The QR code. All right, so that's it, ladies and gentlemen. If there is no other question, can end it here. So we'll pick up on Sunday with chemistry. All right.
All right, sir.
All right, so hopefully you got something useful from this session that you can use. All right.